genuinely understand the iterator follower paradigm, I think lessons 5, 6 should be relatively simple. So that's pretty nice. Maybe tagging mechanics could be a bit complex, maybe parallel metrics could be a bit complex, but definitely 5 and 6 I think aren't super complex if we really understand the iterator follower paradigm. Alright, so before we actually talk about what Lerp is, let me talk about something called functor interpolation. Maybe a bit complex word, but it's actually quite simple. So let's say we have two functors of the same type. So you have A, it's a circle, and B, it's a circle. Now, A and B are very, very similar, but they're slightly different, right? It's the same type, it has like the same stroke, has the same tag, but the radius differs and the center differs. So what if there's a way where I can interpolate between them? And the way I'm going to interpolate between them is that since they're the same type, I'll create a new circle, but its center is interpolated from here to here, its radius is interpolated from here to here, and its tag and stroke are interpolated, but in this case, since the tag and stroke are equal, nothing's done. Oh, and if you're curious, interpolation just basically means the blending. It's going from point A to point B in a smooth fashion. Okay, so again, if we have the interpolation factor is between 0 and 1. If we have that set to 0.25, in this case, that's the same thing as saying center should be 0.25 because we're just interpolating this x from 0 to 1, but the radius would be 1.5 because we're interpolating from 1 to 3, and 0.25 times 2 is, of course, 0.5, so that's where we get the 1.5. Okay, for full semantics, you can read the documentation, but at its core, the idea is if we have two functors of the same type, let me recursively interpolate the attributes. Okay, so now what if we saw a few follower animations already, we saw transform, we saw write, we saw set, but what if we have a new follower animation that just does what we just said, where it's going to interpolate between the follower and iterator using functor interpolation? Okay, so in particular, the really good example of why this is important is rotating. Because transform works, the way transform works is it's a point-to-point algorithm. It'll just say, here's one point, here's another point, let me take the shortest path. The problem with that, though, is that in certain cases, the intermediates, it always looks nice, but it might not be exactly what we want. So let's see over here. Oops. Okay, so that should be trans and oops. All right. So we see that with lerps, with lerping, we see that this is an actual rotation we like. This is the actual rotation we like. Versus when we transform, we can see that it's. Let me actually move this to a different slide. We can see that with transform, it's doing this weird squishing thing, right? It's doing this weird squishing thing, and the squishing thing becomes even more apparent if instead of 5 times pi over 4, let's just do pi. I think it'll become even more apparent then. Yeah, and then it doesn't even look like a rotation at all because it's doing that point-to-point algorithm. Versus with lerps, let's see why it's doing what we want. Okay, so the idea here is instead of actually doing some point-to-point interpolation, what I'll do is I'll have a rotated functor, and then I want to interpolate the rotation factor. So what I'm going to do is I'm going to set lerps to be this rotated. It's initially the rotation is going to be 0, right? Because initially we just want it to be just its regular state. But then afterwards, what I want to do is let me set the rotation factor to be 5 times pi over 4. And now what lerps is going to do is it's going to say, hey, the original follower, the follower is at this state right now, the original follower was a rotated functor and its rotation was 0. Well, now the iterator hasn't changed type. The iterator is a rotated functor and its rotation is 5 times pi over 4. Everything else about them is the exact same. So all lerp is going to do is going to say, at each point in time, let me interpolate the rotation factor and display the output in mesh. And that's all it does. And it looks quite nice. So there's definitely other use cases as well as lerps, but this is just an example of how transform, it's very nice, it's convenient, but it's a point-to-point algorithm. It doesn't take any information about the types involved. So the path it takes might not be what we want, versus with lerp, we get more control, albeit sometimes we have to write a bit more code. Okay, so this is a more easy comparison function. I slightly modified it so that they're next to each other. Okay, so where Lerp really shines is when we get to do user-created functions. Because when you have user-created functions, I can Lerp on the parameters we defined. Okay, so let's actually take an example of this. So let's say we have the Weierstrass function. So I have the Weierstrass function, and I can define it using a and b, just like this is just a regular functor, right? It's just an explicit function, and then at every single point, I'm going to do some calculation. Don't worry about it too much. It actually is an interesting function if you are interested, but don't worry about it too much for sake of example. So now, yeah, okay, I guess it's glitching. So now we have our tree, and initially, this a value, again, we don't even really have to care about what the a value is, but we just know it's some parameter of the function, and then it has some b value, which is 0.1. The axis is just for setup, don't worry about it. Okay, so now I'm going to set the w, I'm going to set the Weierstrass function, and this is important, because if I didn't set it, the follower would be in the empty state, and if the follower is in the empty state, we can't Lerp from the empty state to a Weierstrass function. It doesn't make sense to Lerp because they're not the same type. So I need to make sure I'm setting it so that the follower is originally in the right state. And then afterwards, I'm going to set the b value, some parameter. Don't worry about it too much. I'm going to set the b parameter to 4. And now, at every single point in time, the b parameter is going to be interpolated from 0.1 to 4. So let's actually see how that looks. And we get this cool thing. And again, it's not a point-to-point. It's actually interpolating this factor, and we get this cool animation. Okay, let's see if we have more. Okay, other thing is that we can kind of do this. That was a continuous interpolation, and always Lerp will do a continuous interpolation, but we can mimic it to be discrete. And how I'm going to do that is I'm going to take in this continuous value n, so n could be a decimal, but I'll just round it. And if I round it, it just works out. So over here, the idea is that I'm going to have roots of unity, and obviously we can't have an odd amount or a non-integer amount of roots of unity. So what I'll do is I'll just round it, and let's just actually take a look at the result. Right, and we get, it's always discrete. Very nice. So this is useful for simulations, for example, when you want to, say, interpolate from zero trials to 10,000 trials. And obviously we have to have an integer amount of trials, so just rounding it does the job. Okay, so the other thing is, remember that when we do functor interpolation, it doesn't care about the points, it cares about the type. It cares about the type. So here's an example where we can't interpolate that. Let's actually just take a look at how this looks like. So this looks like a square, right? This polygon, it looks like a square. And then this guy also looks like a square, but we can't interpolate them because they're different types. How do I interpolate between a polygon and a square? It just doesn't make sense. So that's one thing to know, is that Lerp needs the types to be the same. It doesn't care anything about visuals. If you do want to interpolate between these two different types, maybe we can use transform instead. But again, that's not doing anything with type information. Lerp is all about type information, transform is all about point information. Alright, if you are interested, over here I talk about how we can actually make the monochrome intro video. Maybe we can just play it in monochrome for now, but I'll not go over that just for sake of time. But here it is. It should also be included in the default installation.